Okay, so we are next ready to start this new section, linear congruences. So let us start by considering a linear congruence. Ax congruent to b modulo n. Now let's talk about the conditions on these symbols. A, b and n are integers, of course, where a is not divisible by n, so that this side does not get reduced to 0. A is not divisible by n and n is a positive integer. B is some integer, positive, negative, it can be anything. In fact, a also can be negative. And x is the unknown. Because x occurs as simply x, as the first power of x, not x square, not x cube. That's why this congruence is called a linear congruence. In one variable, of course, you may have more than one variable, but this is the simplest case and we are considering this first. Now, for such a congruence, what does it mean to say that something is a solution? We say that an integer x naught is a solution of the above congruence if, of course, Ax naught is congruent to B mod n. All right. Now let us see what this actually means. We already know what it means, but let's see once more. Let's see how far we can go starting from this condition. Let us unpack this condition. This is equivalent to what? This relation that n divides Ax naught minus b. This in turn is equivalent to having Ax naught minus b is equal to ny naught for some integer y naught, right? So this implies this. Conversely, of course, if you have something like this for some integer y naught and for some integer x naught, then you can go back to that congruence. This means what? This means that this congruence having a solution is equivalent to a Diophantine equation having a solution. So solvability of our linear congruence has been reduced to solvability of a Diophantine equation. Which Diophantine equation? Ax minus ny equal to b. We can rearrange the terms a little bit so that it looks like our standard Diophantine equation. So the congruence has a solution if and only if the following Diophantine equation has a solution. This Diophantine equation, ax minus ny equal to b. And you may remember that after proving some results on greatest common divisors of integers, in fact, after having that Euclidean algorithm which allows us to express the GCD of two integers as a linear combination of those integers. From that result, we developed a theory of solving a Diophantine equation like this. And we can now apply that theory to this situation. And we did this in chapter 2. From that theory itself, we will be able to say when a given linear congruence is solvable, and then we will also see what its solutions can be. However, what exactly shall we mean when we say solutions, plural, solutions of a linear congruence? See, here the thing is this. It is convenient to consider two solutions, x1 and x2 of the congruence equal, equal within quotes because literally they may not be equal, if x1 is congruent to x2 mod n. If this happens, then we will not regard x1 and x2 as different solutions. For us, solutions that are congruent to each other modulo n will be considered as only one solution. Although the actual values may be different integers. For example, both 3 and minus 9 are solutions of a linear congruence. Both 3 and minus 9 are solutions of the congruence 3x congruent to 9 modulo 12. And you can verify also. For 3 it's almost obvious because 3 times 3 is 9 and 9 of course is congruent to 9 mod 12. And for minus 9 you have to see the condition. You will see that 12 divides 3 times minus 9 minus 9. In fact, you can see that also almost immediately. So, how will you see? You do not need to actually carry out multiplication or anything. You want this to happen, right? It's the same as requiring this minus 9, right? So, in this integer, what you can do, you can take minus 9 common out, or you can simply see it this way. 1 minus 9 and 3 minus 9s give you 4 minus 9s. From this 9, 1 3 will come and you already have 4, and that is why 12 divides this. And that's why besides 3, minus 9 is also a solution of this congruence. But since 3 itself is actually congruent to minus 9, modulo 12, so these two solutions are regarded to be 1. They are not considered to be different solutions. They are considered as the same solution. Solutions which, however, are not congruent to each other will be considered different. In other words, so what that ultimately means is this. When we say the number of solutions of a congruence, we mean the number of mutually incongruent solutions. This means that, say, for some congruence, you have 3 solutions and they are regarded as different solutions, actually 3 solutions. That will mean that if you pick any 2 of them, they will not be congruent to each other, modulo whatever modulus you have. Okay, so with this in mind, we are going to, whenever we say number of solutions of a congruence, it will mean mutually incongruent solutions, modulo n if n is the modulus. And with this understanding, we can now state and prove the fundamental theorem of such congruences and their solutions, which is this next thing. This is theorem 4.7. It is stated like this. The linear congruence Ax congruent to B mod n has a solution if and only if D divides B. B is this integer, where D is the GCD of the coefficient A and the modulus n. Okay, this is the condition for solvability of such a congruence. Such congruences will not always be solvable. They will be solvable if and only if this happens. Precisely when this happens, then they will be solvable. Otherwise not. And what can we say about the solutions when this condition is satisfied? When D divides B, the above congruence has exactly D mutually incongruent solutions modulo n. Or with that convention that distinct solutions are considered to be the ones which are mutually incongruent, can simply say that this congruence has exactly D solutions. That's it. Has exactly D, but we do write in detail, okay, mutually incongruent solutions modulo n. Let us now see how to prove this. The heavy part of the proof has already been done in chapter 2. We know from our preliminary discussion today, we know that the congruence Ax congruent to B mod n has a solution if and only if the Diophantine equation has a solution. The Diophantine equation Ax minus ny equal to B has a solution. And we know when such an equation has a solution precisely. So, by, and now we need to recall a result from chapter 2 which tells us just that. And that result is 2.9. By theorem 2.9, Ax minus ny equal to B has a solution if and only if D divides B, where same D is the GCD of A and N. That means we practically did not have to do anything. We are just getting whatever we want directly from this theorem 2.9. But that's not all, of course. We need to also next show that there are precisely D incongruent solutions modulo n of the congruence. Now let D divide B so that we have at least one solution. At least one solution of what? Of the Diophantine equation. Let us first see that, because it's from there only we can say something. That is something which is available to us. Let x naught comma y naught be a specific solution, but be clear about solution of what? Of the equation Ax minus ny equal to B, i.e. Ax naught minus ny naught is equal to B. Now from that same theorem, we then know how to write all the other solutions. Once you have one solution of a Diophantine equation, you can write the other solutions, and we know how to write them. In fact, we know from Theorem 2.9 that the general solution of our Diophantine equation is going to be looking like this. Is, let me write like this, x equal to x naught. So in terms of that specific particular solution, we can write all the solutions like this: n divided by d times t, that's the x part, and the y part is this, where t is any integer. T belongs to the set of integers. For every integer t, you will get one solution. Okay. Now, you may suddenly think that I have made a mistake in writing these general formulas, because you may remember that in Theorem 2.9, one part is positive and the other part is negative. Yes, that is true. But do not forget that in that theorem, we had ax plus by equal to c. Here, in place of ax, you have a, but in place of b, you have minus n. So that's why there is no minus that you are seeing here. Okay, so these are the solutions. Now, these are the solutions of what? Of the Diophantine equation. Corresponding to each solution, we are going to get one solution of our linear congruence, and those solutions have nothing to do with this y part, because we need only x. So these are the solutions. However, you can choose infinitely many integers t, but we need to show that there are exactly d solutions of our congruence that are mutually incongruent to one another modulo n. Now we are going to take some very special values of t, d in number. Before that, let's just mention this. Each x equal to x naught plus n over d times t. Each x means for each value of t is a solution. Is a solution of ax congruent to b mod n. In particular, let us take the first d non-negative integer values of t. That means t starts with 0. Now, if you take t equal to 0, you are going to get x naught. If you take t equal to 1, you will get x naught plus n over d. Taking t equal to 2, you get x naught plus 2n over d, and continuing like this, taking t equal to d minus 1, you get this. So these are also solutions. All right. Now we claim that these D solutions, why D in number? Because if you start counting from here, 1, 2, 3 like that up to D minus 1 plus this extra one. So in total we are looking at D integers. We claim that these are mutually incongruent to one another modulo n. But contrary to that claim, suppose that two distinct numbers from here are congruent to each other mod n, and then let's see what goes wrong. Suppose that for some integers t1 and t2, where they are non-negative and satisfy these inequalities, we have this, say, x naught plus n over d t2 is congruent to x naught plus n over d t1 mod n. What will happen then? Then clearly, first of all, you can cancel x naught, okay, using properties of congruences from both sides, and that will give you this. T1 is congruent to n over d, sorry, this is T2, does not really matter, but let me write it like this, mod n. Now we are going to recall, now you cannot just simply just cancel n over d from both sides, because this is product, not sum. So here you have to be careful. And in order to do this cancellation, we are going to recall a previous result. And that result is Theorem 4.3. Let's recall Theorem 4.3, okay. In Theorem 4.3, we have something like this. CA congruent to CB mod n. You want to cancel C from both sides. You can do so, but you then have to compensate for that by changing the modulus n. It is no longer n. It is going to be n divided by d, where d is the GCD of C and n. This is Theorem 4.3. Here also we have SC, which is n over d, and we have our n. So that means if you do not write n over d, if you simply write T2 congruent to T1, you will then have to divide n by the GCD of n and n over d. Now d being the GCD of n and a already divides n, and in fact that's why this congruence makes sense, that n over d is an integer. But even more than that, n over d itself also divides n. And that's why the GCD of n and n over d is n over d itself. Since this is equal to n over d, it follows from Theorem 4.3 that T2 is congruent to T1 mod, now what will you write? N divided by D, here that GCD itself is N divided by D. That means N divided by D, or T2 is congruent to T1 modulo D. But will it be okay? It will not be okay actually due to these inequalities. This means, but before we use those inequalities though, let's write what it means. This means D divides T2 minus T1, but 0 is less than T2 minus T1. Why? Because T1 is less than T2. So T2 minus T1 is positive. And again, because T1 is non-negative, so subtracting T1 from T2 will possibly make it smaller than T2 or not. If T1 is 0, then this will remain T2, otherwise it will be less than T2 because in that case T1 is positive. And T2 itself is less than or equal to D minus 1, which is less than D. Now you look at the 0 part and the D part. T2 minus T1 is the positive integer and is less than D. So obviously it cannot be divisible by D, and that's the contradiction. This is a contradiction. So our supposition is wrong. That means for no such T1 and T2 can the corresponding solutions be congruent to each other mod n, i.e. the solutions x naught plus n over d are mutually incongruent to one another modulo n. Now are we over? No, we are still not over. Because we have shown that there are D incongruent solutions modulo n, but who is saying that there is not any more? Maybe because we have just shown that these are incongruent to one another, right? But maybe outside of this list there are more incongruent solutions. So now we will have to show that no, that is not possible. If you stick to these solutions, you essentially have all the solutions, in the sense that any other solution, possible solution of our congruence, will be congruent to exactly one of these, D. And we do not regard congruent solutions as different. We have already made that convention. But let's complete the sentence. Incongruent to one another modulo n. Now consider any solution of our congruence. Now we do know, however, how the general solution looks. The general solution is going to look like this, where T is an integer. Okay. Now t may be negative, t may be positive, t may also be 0. If however t is 0, we just get this. But I am just saying that t can be any integer. And we can divide t by this GCD d using the division algorithm. And we can do so because d after all is positive by the division algorithm. Some people call this division algorithm itself Euclidean algorithm. So you just know what I mean by this, or what we mean in this book. It is that algorithm which gives us a quotient and a remainder, that thing. By the division algorithm, there exist integers q are such that when you divide t by d, q acts as the quotient and r is the remainder. And of course, r is non-negative and less than d. Now this, instead of this less than d part, you can also write less than or equal to d minus 1, same thing, because we are dealing with integers. Now, with this new information, what happens to our solution? If we now substitute this expression for t there, what shall we get? X naught plus n over d times t is equal to x naught plus n over d times qd plus r. Now, rewriting means rearranging the things slightly differently. If you do the multiplication, you will get nq, and along with that you get x naught plus n over d times r. And this minus this is divisible by n because that is nq. And that is why this thing is, or this thing, same thing, is congruent to x naught plus n over d times r modulo n. However, now if you look at the values of r, these are precisely those values of t which we considered after writing the general solution, which in fact gave us those t incongruent solutions, mutually incongruent solutions modulo n. So whatever you have here is actually one of those solutions, and that's what we wanted to show. Any general solution for some given t will be congruent to exactly one of those solutions. I keep saying exactly one because it cannot be simultaneously congruent to two such solutions because they are incongruent to each other. Okay, and congruence is an equivalence relation. This means, since we are writing so much, let's complete this. This means that the solutions x naught plus n over dt, where t satisfies these inequalities, are the only incongruent solutions. And that way we now know that there are exactly d incongruent solutions. Now we are finally done. The only incongruent solutions modulo n. So you can complete the proof by writing, hence there are exactly d incongruent solutions modulo n. I'm completing it here itself. All right, and there is a very nice corollary. I mean, our result is quite general, right? Now, if we put restriction on that GCD itself, GCD of A and N, which is our D, if A and N are relatively prime, that is, say their GCD is 1, that means in the present context, D is now 1, then the congruence AX congruent to B mod N has a unique solution. Unique in the sense of being incongruent modulo N. Okay, that actually there may be many solutions, infinitely many, but all of them are going to be congruent to one another modulo N. Now, how are we getting this corollary from the above theorem? First of all, here D is 1. So, regardless of what B is, D is always going to divide B because it is 1, 1 divides every integer, and that is why the condition for solvability is satisfied. For this congruence, it will have a solution. How many incongruent solutions? D incongruent solutions. That means in this case only one incongruent solution. So, that way we get a unique solution. Okay. Now, let us see these things with two examples and complete our discussion tonight. The examples we have are quite simple, but they nicely illustrate what these results are about. The first one is example 4.6. In this, we have this linear congruence 18x congruent to 30 and the modulus is 42. Alright. So, what will you do first? To even know whether the congruence has a solution, you need to first of all calculate the GCD of 18 and 42 and see if it divides 30. Because now our A is 18, N is 42 and B is 30. GCD of 18 and 42, you can check that it is 6. Since 6 divides 30, the above congruence is solvable. Solvable means has a solution. Now, how to find a solution? To find a solution, you can simply try to find a solution by inspection. However, just from this 6 itself, we know one thing immediately. Not only that there is a solution, but actually there are exactly 6 incongruent solutions. And by inspection, one can find one of them to be 4. It is hard to say in general how to go for this guess. You just have to put values and see if the congruence is satisfied. That crude method, however, may not work when the numbers involved are extremely large because the computational labor may be too much. But we are going to see something about that. Okay. So right now, let's just assume that just looking at the various values, one comes up with 4. So 4 is a solution. Now using 4, we can however write the other solutions, the other 5 incongruent solutions modulo 42 using our theory. So what will be the other solutions? Oh, by the way, what is n here? N is 42. This is d. So what is n divided by d? It is 7. That means the other solutions, and in fact all the solutions are going to look like this, plus 7t. If you take t equal to 0, you get this solution. Taking t equal to 1 means what? Adding 7 to 4, you get the another solution, 11. Taking t equal to 2 means adding another 7 to this, that is 18. Then adding another 7, which means what? 25. How many have we got so far? 1, 2, 3, 4, 2 more. Adding another 7, 32, and adding another 7, finally we get 39. So these are the 6 solutions of this above congruence modulo 42 which are incongruent to one another. Any other solution you find of this congruence is going to be congruent to exactly one of them, modulo 42. Have I got the values correctly? Let me just simply check. Okay, I am infamous for making simple mistakes like this when it comes to numerical values. 4, 11, 18, 25, 32, 39. Yeah, okay. Let's see another one. So it's not really extremely difficult or anything. The only difficult part we see here is guessing this first solution. You can actually guess any solution here. Okay, keep that in mind. Instead of taking x naught equal to 4, yeah, this will be a nice exercise. So what you do, say you have not got x naught equal to 4 first, say by inspection, because you may have started with quite large values of x, you found this value first. Say this is your another x naught. This is your x naught, say, not the author's x naught. With this x naught also, the theory tells us that all the solutions are going to look like this. You find all the solutions with this x naught, and the numbers that you will get may not be exactly these numbers, but you will see that each such number will be congruent to exactly one of these numbers. So that essentially when it comes to considering integers congruent to each other as same, you get the same set of solutions. Okay, that's the point. Next, example 4.7. Here you have 9x congruent to 21 mod 30. Again we have to find the GCD of 9 and 30. GCD of 9 and 30 turns out to be 3, and 3 definitely divides 21. So that means this is a solvable congruence. Now the numbers involved here were also large. Here also they are somewhat large. You can simplify this congruence by using theorem 4.3. In other words, you can cancel from both sides. On this side you have 3 times 3x. On this side also you have 3 times 7. Let me write them like this. 3 times 3x is congruent to 3 times 7 mod 30. Now if you cancel, and write this, then you know you have to compensate for that by dividing 30 by what? By the GCD of 3 and 30. And the GCD of 3 and 30 is what? 3, because 3 divides 30. So if you divide 30 by 3, you will have the new modulus 10. This means what? This means that any solution of that original congruence will automatically be a solution of this new congruence. But is the converse also true? Yeah, of course true. If you find an integer x that satisfies this congruence, you can multiply both sides by 3 always. See, multiplying a congruence by something, in fact, it is always true. However, we are not merely multiplying the congruence on both sides by 3, but we are actually multiplying everything by 3, even the modulus. Does it make sense? This implication is justified by Theorem 4.3, but we are now saying that we can go back also. What does this mean? This means 10 dividing 3x minus 7. Or if I want to write it in an equation form, 10y is equal to 3x minus 7 for some integer y. Now you divide both sides of this equation by 3. That will give you what? 30y equal to 9x minus 21. That in turn means that 30 divides 9x minus 21, and so 9x is congruent to 21 got 30 for that x. So yes, we can go back. And that is why now that we know that this congruence is solvable, the next job is to find that specific solution. And for that, we won't work with the original congruence, but this slightly simpler congruence. Now we have to find one solution. And then there will be 2 more incongruent solutions, because the total number of incongruent solutions will be this GCD 3. Now finding one solution of this congruence is actually rather easy. Note that if you take x equal to minus 1, then you get minus 3 here on this side. Minus 3 is in fact congruent to 7 mod 10, because their difference is either 10 or minus 10, which is divisible by 10. So one solution is x equal to minus 1, but because minus looks a little, there is no problem, but still we prefer positive values. So in place of minus 1, you can write 9, because they are congruent to each other mod 10. So although guessing 9 is somewhat difficult, but guessing minus 1 is quite easy. But you are anyway going to get that 9. So one of the solutions is 9. Now what about the other solutions? With 9, you have to add what? X naught plus n over d, n divided by d times t. N is 30, d is 3. That means 10t. So with x naught first you add 10, that gives you 19. That is one solution, an extra solution, and another 10, 29. So these are the only 3 incongruent solutions modulo 30. You may get other sets of 3 solutions, but those sets in one way or another is going to be congruent to the numbers of this set. Okay, so any such number of 3 incongruent solutions can be taken as your solution set. Now, instead of using this ad hoc guessing method, you can also go systematically using the theory of GCD. You remember that we can express the GCD as a linear combination of the original numbers, and in fact that's what the author did here. You can express the GCD 3 as a linear combination of 9 and 30 in this way. 9 times minus 3 plus 30 times 1. And why do I say that this is systematic? This itself looks like a guesswork, no? At first. How do I know we have minus 3 here and we have 1 here? Well, you apply the Euclidean algorithm to find the GCD of 9 and 30. And then you do the back calculation. That will give you this expression. You know all these things. Okay, we already did this way before. So now what we do, we do not, however, need 3 here, but we need 21. So we will multiply both sides by 7. That way we will get 21 equal to 9 times minus 21 plus 30 times 7. And this implies what? This implies 9 times minus 21 is congruent to 21 mod 30. That means one of the solutions can be taken as minus 21. Okay. X naught is minus 21. Is that our original congruence? Yes. 9 times x is congruent to 21 mod 30. But if you look carefully, this itself is actually congruent to 9 mod 30. Yes. So you get back this itself. So the point here is that if the numbers involved are really quite large, so that guessing will most likely fail or will take so long that it becomes prohibitive. It is prohibitively long. In that case, you can instead follow this systematic method of first finding, see, in those cases where the numbers are large, finding the GCD also will be quite a heavy task. So you systematically apply the Euclidean algorithm to find the GCD, then do the back calculation to have this, and then you have one solution, and then from that you write the other solution. Okay, so that would be a systematic approach. And with this, let me just end today's discussion. After this, we have systems of linear congruences, where we will have, in place of one, many, finitely many linear congruences in one variable, of course. And we will see something called the Chinese remainder theorem. And then we will see what else comes after that. What do we have tomorrow? Oh, tomorrow we have trigonometry for class 11. Okay, so see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.